let's start with previously, okay? As always. So what did we do last time? Nothing. Curves. Good. Curves. And let me just explain things. Curvature. What else? So let me just explain it without formulas, okay? What curves are, okay? So first of all, we need a map from an interval how to the plane, okay? How to do it? How do we do that when we don't know mathematics? What would be a good way to say what the curve is? A map from an interval to R2. Do you have an example for me? A circle. No, I mean, if you don't know math at all, how would you do a curve? How would you make a curve? Draw, we can draw it. Yes, like this, right? And we draw lots of curves, right? These are curves. Good. And so the idea you should have in mind is if you have just a piece of thread, like this, okay? Well, this is elastic, which is bad. Well, it's a closed curve, if you like. You can stretch it, you can squeeze it. Well, not too much, but here you can stretch on one side, but not on the other. Okay, that would be different parameterization of the curve, yeah? Okay? So that would be an idea of how to do that. So now, when we talk about the tangent vector, we are talking about something like this, which has unit length. Yeah? The direction I'm looking at. Okay? And this one here, we can call it the speed, but also just the stretch factor of the curve. I mean, there are many ways to describe it. Either you have a road, right, and you drive a car through this. You can have something like this, elastic band, and then just, have a curve. And how much you stretch, that exactly is the length of hair, yeah, at every point, okay? Now, what does arc length mean? These are the different words we had last time. That means we have a curve made of thread without stretching. Stretch or squeeze, okay? So without, just like this, I don't stretch, I don't squeeze it, and that's how my curve looked like, okay? And then we had curvature, yes. That is when you go on the road, where to put your, I forgot the word again. There's dot wheel of a car, okay? And when you turn to the right, you have negative curvature. You turn to the right. Because mathematicians like to turn to the left, right? This is turning to the left. It's a positive direction, okay? Positive. If turn to the left, okay? So we have, as mathematicians, we have a natural orientation, which is turning to the left, okay? And then, of course, there's some problems when you change the directions. I mean, meaning change the turns. What do I mean by problems? Okay? You have a kappa. The curvature is normally the curvature of a circle, how it's bent. And you could actually just do the curvature, just taking the absolute value. But whenever the thing hits 0, I have a non-smooth function. right? Because it would look like this whenever it's changed sign. Okay, so that's why it's kind of important that we have some type of oriented curvature so that curvature is still smooth. So some textbooks actually call this one the curvature. Okay? And this change of sign, how does it look like? Anyone an idea how you can identify a point where, you know, instead of turning to the left, you turn to the right and the other way around? How would such a point look like? Can you draw it? Yeah, so I'm turning to the left all the time, yeah, with my curve, and now I need to turn to the right. How would such a curve look like? Well, I have to do that at the point where I change my directions. Draw it. Yes, exactly. So this would be an inflection point. Okay, inflection point. And I think this should be an X. Yeah. Right? So basically, it looks like X to the 3, yeah? Why? Because the curvature is second derivative, and second derivative should be 0. Okay, it should look like such a thing. Okay? Good. Now that's what we had done last time without formulas, basically. Okay? So we wanted to describe curves, and we said, if I tell you how you turn, okay, and the speed is always the same, I can get my curve back because I just tell you how to drive. If you're blind on the road, and I would tell you when to turn left and when to the right, you will arrive at your destination, right? Yeah. There's no problem with that. That's basically what this theorem says. Okay? Okay, cool. Now, we wanted to do some discrete curves. What could a discrete curve be? Discrete? Well, wait. Wait, let me, discrete. That should be this way, curve. Okay, what could that be? And why would we want to do that? Why would you want to have discrete curves? Okay, 为什么? Okay, we want to discretize. Wait, but what is discrete in Chinese?
离散的。
Okay, 离散的一个曲线。Okay, 为什么需要这个东西？这是第一。
Show the mean for example, each one of the point between shows the mean the mean length of a given prime.
For example, so where do you apply such a thing? What do you think?
So you mean discrete curve?
Yes.
From the map from
I mean, first of all, why would people be interested in that? Okay, what you know, just very naive, right? Why would someone do discrete curves? I mean, how would the discrete curve look like?
Some discrete point in R2.
Can you draw it for me?
The discrete point. Okay.
Yes, and then?
This is a map from and for example, Z plus like that to R2.
What would you do with points, by the way?
You can just think it as a kind of some discrete points on the smooth curve. So the distance of each one gives us the kind of mean the mean length of for example this gamma. This is the mean length of gamma prime.
For example, one could do that. Okay. So one way to think about discrete curves is because you want to play computer games, you want to draw a curve in the computer. Okay? A computer cannot draw infinitely many points, right? Right? So what does a computer do instead?
They give some finite points and consider their physics.
I consider some finite point, and what do I do with the finite points?
Just like
Oh, wait a sec. What do you want to say? You don't want to say anything?
The original kind of method is to draw the segment between those points. But they have a question. For example, we have this kind, but it looks really sharp, not smooth. So instead, we consider the
I think with
like that, the Bezier curve.
yes, but the information is the same, right? Because
Yes.
it's made out of these points. So it doesn't matter whether you connect with this one or that one because it's just a matter of optics, but it doesn't change the mathematics. Okay. So what the computer does, as I said, is you take finitely many points, and actually the easiest way is just to connect with segments.
Yeah.
Because there's no, you can do all sorts of things in between, right? Can make it rounder or whatever, but it doesn't change the mathematics. So we take the segments, it's the same, okay? Because you don't have more information once you want unique something. So instead of this smooth curve, we will have a collection of points which we could connect with segments, okay? That would be a curve. That is not smooth, but it's a discrete curve.
It's smooth.
Huh?
Bezier curve.
Yes, what is the difference mathematically? Because you want just 3 points and you want to somehow put a unique curve in between, right? Yeah. So whether it's a segment, whether it's... So now the question is, when you have such a thing, okay, how to define curvature? How to define everything what we defined here in this world?
Maybe.
Wait a sec. Let people think. So when you have, so the discrete, let me just write it down. It's just a collection of points, okay? It's just some type of okay? Well, let's say 0, 1, and 2, R2. Gamma of n, okay? I call it gamma k, and these are k points. Like this, yeah. And we connect this thing with, that's my gamma, okay? That's, okay? So, it's very natural to say, this is gamma k plus 1, this is gamma k, so the difference between these two is something like our tangent vector, right?
Yeah.
Oh. We can call it delta, if you like, and the norm of it, or length of it, is a tangent vector. Well, it's not quite true because we don't have length 1, yeah. But it's not the it's just the derivative, the direction. Okay, so it's like something like that. Okay, but the question now is, how would you do curvature? We don't have a smooth curve, right? We have these edges and we have these vertices. And now we want something similar to the smooth case.
Instead of thinking like kind of rotation, you think it as the circle just between it, the radius of the circle between it.
Yeah. So
one of the radius, and so the circle can be given at the 3 points. So you can consider for gamma k and consider the circle's radius from gamma k minus 1, gamma k and gamma k cross.
that's one solution, but what is the circle determined by 3 points? So the idea is, that's correct. Take 1 over r of a circle approximating the curve. In the sense, because if you have take 3 neighboring points like this defines me a triangle. Always. Okay? Now, how many curves, how many circles are there at least? Yeah? Is it uniquely determined? No. The question is, if I have such a triangle, what is the choice of a circle?
Only one.
There's one which does what?
Just approximate the curve. The curve is straight.
Yes, but what is the one circle doing? How do you define a circle here?
To be a circle who
What is a circle? If you have 3 points, how do you get a circle? Yeah, how to get a circle. How does, you have a triangle. How many circles are associated to a triangle?
we can. This is the contain. Let that be a prime equals a prime c and ab prime equals prime c. A c prime equals c prime b. And we make L1, L2, L3. This
Perpendicular. It's a hard to pronounce word. Yes.
And this is 圆心.
Yeah, center of the circle, yes.
And OB is D. Now we.
The drawing went wrong.
The center may not be inside the circle.
Yes, sure. But in his example, it does.
No.
No, it's smaller than 90, right? It's smaller than 90, let's say.
Absolutely.
I think it's smaller than 90. It's okay.
No, that's not the parallel center. Perpendicular center. That's the opposite not. Yeah. It's center. No. It's the opposite.
This one? That's okay?
No.
Yeah. Yeah, that's fine. You can do that. Just draw the circle. Just draw a circle. It's fine. 只是画着对，没有画好，不过 it's okay. Just draw the circle as well. It's okay. 对，我 I guess so. Yeah, it was not bad, but I mean, yeah, it's all good. Okay? So that's a possibility. What else? Okay? This is called circumcircle. What else? By the way, just give me a formula how to compute the radius here, or d. from from the length of the edges. Okay? So length of the edge is something we have because that's this information here on the curve, right? So how to compute that? That's one question.
Just like BC over
And
A.
other circles. Think about it for 5 minutes or so. Just take your time. Huh? You have it? So you have 3 points. It's gamma k minus 1, gamma k, oh, just not here, gamma k and gamma k plus 1. It defines me a triangle, okay? And I know the edges because that's my curve, yeah? And I know the angle. Let's call it gamma. Oh, well, alpha might be better. Or phi k, okay? So I would like to have a formula which says kappa k, right, in terms of the angle. Why? Because obviously angle is what makes the curvature, right? So now the question is how to compute the thing in terms of that particular angle, right? So what we need is to compute the radius of the circle, right? And maybe make assumptions, maybe not, on the edge length and so on, maybe not, and compute R. And the idea is the kappa should be 1 over R, right?
Yeah, it should be. Can I write it down?
Sure. And then tell me whether there are other circles as well. This is not the unique choice, right? It's not the most natural choice you can do because it's a discrete thing now. We can attach. You know.
Gamma K, and kappa K equals it's 2 sine of 5K over right K plus gamma K minus 1.
Mm-hmm.
Yeah, because,
Why?
Because for example, we have a circle A, B, C, so we know that over what did I say? A, B, and C, so that A over sine of A is 2 radius.
What is A? Yes.
Can you see? Sine of the angle A equals 2R. So BC over 2 sine of over BAC equals 2 equals R. So plug in the kappa K is 1 over R. Has because this equals gamma K minus 1. Gamma K plus 1.
Do you know the formula? All of you?
Yeah.
All of you know. Perfect. Okay, so that's one possibility. Okay? So, one possibility. So curvature basically is sine of the angle over length, right? So you see, there's a slight discomfort here in a sense because you need a slightly too much information because you all need to have information on k minus 1 and k plus 1. You know, because you divide by k minus 1, the distance here, right? What you really want to do, because since if you construct a curve, you would know where you are and where you go next, right? But you might not know where you go afterwards, right? In a sense. So that's not it's kind of a local thing because it only depends on 3 points, but it's not quite, right? Something that only depends on neighboring points. So in discrete world, there's always values that you can attach to the vertices and values you can attach to the edges, right? And then, of course, if you have a triangle, values that are well defined on the face. That would go 1 dimension higher. Okay? So functions that living on the vertices are, for example, the map into R2, where the location are. Values that on the edges are directions. Yes? And then area would be something that lives on the face. Okay? Good. What are other possibilities? Is that the only possibility to define a discrete curvature? That's very natural. It's unique. Are there other possibilities?
Kind of other things, maybe for inscribed circle or circle from.
We can do the inscribed circle.
From basic curve.
Yes. Inscribed. Oh my goodness, how to write it? Circle. So what would be the curvature formula in this case for the inscribed circle? is more natural from the curve point of view, right? Because before, when we had a smooth curve, we were doing also some type of rather inscribed circle. So this one is slightly more natural in this sense, okay? The question is how to now compute this R here, right? So we are at, that's why discrete geometry is always like elementary geometry in school, because you have always these triangles and you need to compute. You know how to do it? Yeah, you can have it about it. Just say it, call it alpha. 你就叫它 alpha 可以。
角 B 对应的边不应该是 B 吗？
Yeah.
你说你是不是设错了？这个 AC 边应该一般来讲都是设成 B 的。
没关系，
对，他没事，他这个名字错。It's okay. There's no problem.
你反正你也用到 B， 还不如前面那个。
Well, it's not necessarily, but okay. When we had the smooth curve, 它们是对等的。because we want an arc length, right? Just assume arc length. What happens then? 对，如果是一样长的话，会是什么样的？Why is a sign? Which one would you do one?
If this equals, if AB equals AC, so you have this line and this.
Yes.
So this is, and also this angle equals to this angle, so this angle.
That's correct.
Alpha over 2. So
Yes.
I have that B over 2, it is equals A sine alpha over 2. So B equals 2 alpha, A sine alpha over 2.
Yes.
So now it is.
Ah, okay, you can do it this way. Yeah. Roughly. I think you can make it easier. Okay, it's possible to make it easier. Is there an easier formula? But you can still shorten it. Right? Should I just write it down? You want to just figure it out yourself? Let's just, because we want arc length, let's just assume A is 1. Okay? Perfect. Right here, we have space. 写大的。Can you see it?
We know this two sides is equal and we know.
And cut the triangle into pieces.
Yeah.
把三角形切成片。我切成更多是吧？Like, yeah. Yeah.
Tangent phi k. Phi k is equal. And A is we can plus 3 side and like this. 就是这个不用。
差不多。
we can know 这个1/21是多少？
Okay. So it's something. So the difference, the main difference between these two concepts is here. Well, this circle here, circumcircle, we have sine.
And it's scratch circle.
Yeah, we have sine, and it's slightly bigger, right? So it's a smaller curvature, and here we have something with tangents. Okay, so this is, and it's the curvature is bigger. Okay, okay, but then it's slightly complicated, right, to do it this way because then you don't know where this point here is. Like you have a complicated formula. The other way to do it, I mean that's the third way maybe, but using the same idea is, well, we just mix the two ideas and take the midpoint and take the circle. That's like this. Yeah? That's also another possibility. So this is a half then. And we have that. Like, wait. Yeah, I think 2R. Or 1, I think it's like this rather. Okay? So this would be give a very easy formula for, so basically the one is sine, the other is tangent. None of this is better than the other because we are in a discrete world. There's no proper association. We will have to agree on what the good. We have to agree on what the curvature is. Okay. The advantage here is basically we can take it as a function on the vertex because this only depends on the angle. While this one depends on the angle, but also on the distance, on the length of something. But well, I should say we normalize the length here, right? So it's not quite true. Okay. So now, that's a way to define curvature, and we can reconstruct our curve through curvature. And the idea is, of course, if I have a smooth curve and make a lot of these tiny points on it, all these concepts will converge to the same curvature of the smooth curve. Okay? It's the same. But there's one thing you need to take care of, which is this arc length. Why? Why is it problematic to define arc length on the discrete world and have it converge to arc length in a smooth world? Any idea why this is somehow problematic? How would you define arc length in the discrete world? What does it mean?
That is the distance between gamma k minus 1 and gamma k is equal to gamma k minus gamma k plus y.
Why would that be arc length? It's not length 1. That's just...
And these two are all equal to y.
Okay.
Maybe the arc length.
That could be the arc length, but then the problem is if I have a smooth curve, and then I can just take segments that have length 1, right? So these points are all determined. I cannot take arbitrarily many, right? Yeah. When I want to take a lot, I have to scale the curve, make the curve very, very large. Then I can do this. But without doing that, I can't. So arc length is problematic. It's kind of problematic because it's kind of, you have to scale first, make it very large, and then you can refine. So actually, arc length is not really good in discrete world. You want it to be small, right? Like 1 over n or something that you can actually approximate a finite length curve. Okay? What would be the length, by the way, of the curve?
Length of the curve maybe.
It's some
Huh?
Between gamma k minus or the
Sigma.
sum of k or delta
I
gamma.
to n. Some are from 1 to n. Yes.
Maybe like that, right? Exactly. So this one should not be 1. Otherwise, we have really infinite many curves if we have infinitely many points. Yeah. So, but then sometimes it doesn't really matter. We just take an infinitely long interval. We just take infinitely large curves because we can just scale, right? And scale back again. Okay. So this is discrete curve. The curvature is the only invariant. Now the question, when we have a closed curve, for example, 2 questions. Okay, the last questions for today, because I think so. First, conditions. We need a condition such that a discrete curve is closed. So if you we would do that with your thing that it's, I'm not sure how much of the plating is left, of the toy is left yet, but if you want to make a discrete curve, we want to close up, what are the conditions that it can actually close up? Second, how to compute enclosed area. Okay, so if I have a smooth curve, I would like to compute this enclosed area, meaning the area here. What can I do to do it? And how to use discrete approximations to actually compute. Okay? So this is A here. I mean, you can. The second one you can do for discrete or smooth, right? I mean, do either one if you like.
Oh, by the way, I just forgot what the Picard series. I think that's useful for the question.
Well, what do you mean by Picard theorem, though?
Where we use some integer points in R2 to
Yeah.
to compute the kind of polygon area.
You can do that.
So,
But how to
the
do?
formula?
I don't know. I mean, I don't care. In a sense, you can actually do it yourself, right? Do the formula yourself. You just take a polygon and just compute the area by yourself.
Yeah.
You don't need any formula. 自己想一想。
是不是在那个具体线上是这个东西什么举出的点就是这样？
对，可以。
给它这么变成就是变成然后变成一些直线的，就是
对，可以。
给它变成一些直线的柱和和。
你可以有很多办法，各种各样的。可以想一想是怎么样的最简单。
I have the kind of thinking.
Yeah. Wait. Anyone else with an idea?
I had an idea.
Okay. Do you have an idea as well? Do you want to wait a little bit, and I'll let him wait a little bit. Wait a little. Just wait 2 minutes. 还在。是另外一瓶了吗？还是之前那一瓶？ Is it necessary? Are you looking a formula up in the book? Is it necessary?
你是不是让直面积分？
物理也变换。
I don't think it's necessary.
Teacher, so maybe
Can,
this is so like
Mhm.
this kind of 就是它这块，比如说这块有凹的，然后就把凹的这块给先填平，然后把这部分面积，就是因为如果是这样，就是我们把这个分成几个这种的话，我们把它分成9个做份儿，这样凸的部分就单独这样切出来单独算，就像这个。然后就是如果有一些就是这种如果多个凹的，就是可以这么着给它切出来单独算，然后接下来剩下的它就是，然后如果发现是有凹的部分，就像这种就可以给它填平，然后这样的话我们就保证，因为不可能有多个部分，所以它这个一定是一个凸的，然后这个凸的我们已经知道它函数是给积分算。然后就现在我们假设已经把这些给填平了，然后那这也是个图的函数了。接下来我们找一下，先把它分成2半，然后这一半可以用积分算，这一半也可以用积分算，然后就能算出来。
是的。可是那这个和这个 curve 有什么联系呢？
就是那你说这个 curve 它是，就是
我们有的 information 只是这个 curve 是什么样的 ，right？
就没有它的函数那个。
我们有一定的当然我们有，可是我们有这个是 curve 的那个点，就是 gamma of x 等于什么？那么如果当然是这样就可以啊，因为我们这个课你可以这样的填什么，可是这个数会算出来很麻烦。那我们想要的是个很简单的 formula。
I got one.
What do you have?
I find it.
You found it. Well, that's cheating, right? And then now tell me why.
This we have some theorem, for example, the enclosed area omega. So the partial omega equals.
Okay, write it on the blackboard, and then tell me why.
I have 2 ideas though.
And how you wanted to prove that. Easy, not with anything.
I have 2 ideas. The first one, instead of thinking in this kind of thing, instead of thinking in R2, which was start thinking at the z mod 1 over n z were every were of the form x and y, such that x equals n over something maybe be x prime, where x prime in D, and y is the end of the y prime or y prime in D. Exact. So we have R2. So this is for given n in D plus. For given n, we will consider n points. X1 to xn, such that for some q such that gamma of xi in whatever qn times d squared.
Okay, you can do that.
So
And then?
this time, so it makes just like a polygon.
Yes.
Just like this. And all of them are just like a kind of rational number, but with given.
Is that necessary? And to have rational numbers on here? I mean,
No,
I mean, we don't want.
actually,
Well, you
no.
don't. What we need is finitely many points. We don't need that the values are rational.
Yeah.
Right?
So that in this case that Bn is defined by the number of x and y in whatever q and z squared. Such that there exists alpha and beta. Such that gamma, we can write it gamma x, gamma y. Where gamma x or gamma y, given the interval L to R.
You can do that.
And so that's gamma y alpha equals gamma y beta. And gamma x alpha is less than x less than gamma y beta, gamma x beta. So it just looks like, for example, I say this is in this kind of area. If there is these 2 points in gamma such that they're in the same length, but the x coordinates, this is smaller, this is
That's fine.
this is bigger. So by Picard theorem we have that.
Well, you would need to prove the Picard theorem, right, to use the Picard theorem. I mean, that's the point. If you want to apply theorems, then you have to prove it first.
No.
Can I draw a picture? Let me draw a picture.
A equals -1 plus limit n to infinity, a positive infinity, 1/2n plus what was it called there? BQN or BQN over n squared. Exact. No. N squared. Exact. I think it's not necessary.
Yeah, well, how do you get an easier formula? It's my question. So let me just 1 sec. Yeah, you can. What is the easiest area you can compute? Triangles. What else?
Or
Squares, right? Triangles or squares. So you can choose a point here, and then you can just take points on the curve, right? And say the area is the sum of the area of the triangles.
yeah, this one. Yeah.
And these are our
Break the area down to triangles.
break the area down to triangles.
Yeah.
If you do the formula here, it has one huge advantage because you have, if that's my 0 point, you can choose any point actually, then this value is just gamma k.
Yeah.
Or the length of the edge is just length of gamma k.
Yeah.
And then if you want to make it even simpler, you can actually take the tangent here where it's perpendicular and make these triangles. This one. And at each point you do the same so that it is.
Yeah.
So basically at each point you take the tangent vector to the left and to the right and have many of those triangles. Let me just draw this. Like this.
Yeah.
Why is this advantageous? So, well, it's a good thing to have it. Whoa, like this. 2 of those at each time.
Yeah.
Why is it good? How to compute the area of this triangle? Why is it good to have this triangle? So this one here, wrong chalk. This vector here would be gamma prime, okay? This vector here,
Would be gamma x.
gamma
Gamma t.
k or whatever, or t. Right? So what is the area of that triangle?
Over 2. One of the. One of the 2 of the integral L gamma prime gamma t. Yeah. Yeah.
Like that? And then you would integrate?
Yeah.
And then what are those? If it's not perpendicular, it would be actually just like this, right?
Yeah.
Right? Because the determinant measures double of it. And it just compute this. And then you get your formula. So the formula is just a half determinant of gamma prime over the curve, t, e, I. And if you compute, right, it's gamma 1, gamma 2, or gamma x, gamma y, if you like, gamma prime x, gamma prime y. It's exactly the formula you had, right, with another term, but it's okay. So what I mean is all breaks down to computation of the area of a triangle. Because when you take more refinements, then it will converge to the smoothing.
And I also have another thinking or another idea.
Because it's actually very complicated to do it this way, yeah? You would need
So I
to.
have another idea.
It's not Stokes theorem.
Yeah.
Well, it is Stokes' theorem, right? It is Stokes' theorem, after all, because you are computing some area using the boundary of the area. I mean, if you like this way, it is. But Stokes' theorem is it's just integration. It's nothing else. There's no reason to, there's nothing behind Stokes' theorem other than integration. Yeah? It's just the main theorem of integration, that's all. Yeah? So the only thing here is just the triangles. Okay? Okay, that's all for today.